Right now, you're racing through space at over 600,000 miles per hour. You can't feel it. You never will. But you're being pulled towards something we can barely see. Something massive. Something wrong. We thought we knew where the universe ends. We were wrong. The edge isn't where we believed. It's not even an edge at all. We're about to journey to the cosmic microwave wall, to voids 300 million light-years wide, to galaxies vanishing into darkness, to the truth about boundaries that don't exist. If you're ready to see how trapped we really are, like and subscribe. We begin now. Stand at the edge of the ocean and stare at the horizon. That line where water meets sky isn't the ocean's end. It's just how far you can see. The universe works the same way, except the horizon is 46 billion light-years in every direction. We live inside a bubble, not a real wall, a boundary of information. Every telescope on Earth points outward, capturing light that traveled for billions of years. The Hubble peers into distant galaxies. The James Webb sees even farther, detecting ancient starlight from the universe's infancy. But no matter how powerful our instruments become, there's a limit, a hard stop, not because space ends there, but because light itself has limits. Think of yourself standing in a massive, dark warehouse. You hold a flashlight. The beam illuminates 30 feet in every direction, creating a circle of visibility. Beyond that circle, the warehouse continues. It might stretch for miles, but you'll never see those distant corners unless you walk toward them. Except in the universe, you can't walk anywhere. You're stuck, forever watching the same bubble expand at the speed of light. This bubble is called the observable universe. The key word is observable. Scientists estimate it contains 2 trillion galaxies. Each galaxy holds hundreds of billions of stars. That's more stars than grains of sand on every beach on Earth. Yet this unimaginable vastness is confirmed to be just a fraction of everything that exists. Here's where it gets strange. The universe is 13.8 billion years old. Light has been traveling toward us since the beginning. You'd think the observable universe would be 13.8 billion light-years in radius, but it's not. It's 46 billion light-years. How can light travel farther than time allows? The answer lies in expansion. While light races toward us, space itself stretches. The fabric of the universe grows. Galaxies that emitted light billions of years ago have moved farther away while their light was in transit. By the time that light reaches our telescopes, those galaxies are no longer where they were. They've been carried away by expansion itself. Picture ants walking on a balloon while someone inflates it. The ants move forward, but the balloon's surface expands faster than they walk. They never reach their destination because the destination keeps moving. We're those ants. Every galaxy we observe is like that destination, perpetually retreating. What this means is terrifying and humbling. We see 46 billion light-years in every direction, creating an observable sphere 92 billion light-years across. Beyond that sphere, the universe continues. It might be infinite. It might contain structures we cannot even imagine, galaxies beyond count, phenomena beyond description. But we are trapped inside our bubble, watching the same cosmic neighborhood forever. And the bubble isn't even stable. What comes next makes our cosmic prison even smaller. Light moves at 186,000 miles per second. Nothing in the universe travels faster. This speed limit is confirmed by every experiment, every observation, every physical law we understand. It's the ultimate cosmic rule, and it's exactly what traps us. When you look at a star, you're seeing its past. Light takes time to travel. The nearest star system, Alpha Centauri, is 4 light-years away. When you observe it tonight, you're seeing light that left 4 years ago. If that star exploded yesterday, you wouldn't know for 4 years. You'd keep seeing it shine, completely unaware it's already gone. Scale this up. The Andromeda galaxy sits 2.5 million light-years away. Every photograph shows Andromeda as it was 2.5 million years ago. when early humans were just learning to walk upright on Earth. The galaxy you see doesn't exist anymore, not in that form. Stars have been born. Stars have died. The entire structure has shifted, but you're seeing ancient history, not current reality. This creates a fundamental problem. Information cannot travel faster than light. Nothing can. Not signals, not matter, not even gravity waves. The speed of light isn't just a speed. It's the speed of causality itself. It's how fast the universe allows cause and effect to propagate through space. Now, imagine a galaxy 50 billion light-years away. Light from that galaxy can never reach us, ever, because the space between us and that galaxy is expanding faster than light can cross it. The galaxy exists. It's real. It might contain billions of civilizations, but we are permanently disconnected from it. No information exchange is possible. No observation. No contact. It might as well exist in a different universe entirely. Think of trying to swim upstream in a river that flows faster than you can swim. You kick and paddle with everything you have, but the current pushes you backward. The destination remains forever out of reach. Light from distant galaxies faces the same impossible task. It travels toward us at maximum speed, but space expands faster, carrying those galaxies away into permanent darkness. This is confirmed by observations of galaxy recession velocities. Astronomers measure how fast galaxies move away from us using redshift. The farther away a galaxy is, the faster it recedes. At a certain distance, the recession velocity exceeds light speed. Not because the galaxy moves through space faster than light, but because space itself expands between us and that galaxy. Special relativity says nothing can move through space faster than light. But special relativity says nothing about space itself expanding. That's general relativity's domain. And general relativity allows space to stretch at any rate. There's no speed limit on expansion. What this means is chilling. The observable universe is finite, but the actual universe might be infinite, and most of it is locked away forever, separated from us by expansion we cannot overcome. But the edges of what we can see hold even stranger truths. Sailors see the horizon and know it's an illusion. Sail toward it and it moves. It's always the same distance away, defined by Earth's curve and your eye's position. The cosmic horizon works similarly, except it's defined by light's travel time and space's expansion. Scientists call it the particle horizon. It marks the boundary of everything we could theoretically observe. Calculate the particle horizon and you get a number that shouldn't make sense: 46 billion light-years. Remember, the universe is only 13.8 billion years old. Light should have traveled only 13.8 billion light-years. But expansion stretches the distance. The photons we receive today from the cosmic microwave background were emitted when the universe was just 380,000 years old. At that time, those photons were only 42 million light-years away from where Earth would eventually form. But 13.8 billion years have passed since then. During all that time, space expanded. The regions that emitted those photons have moved away. Today, those regions sit 46 billion light-years distant. The light bridge they sent still reaches us, but the source has retreated to almost incomprehensible distance. Here's the twist that breaks minds. The particle horizon isn't a physical barrier, it's a visibility limit. There's no wall at 46 billion light-years, no membrane, no edge. Space continues beyond it. Galaxies exist there. Stars burn, planets orbit, but their light hasn't had time to reach us yet. They exist in a realm beyond observation. Imagine standing in a massive crowd where everyone lights a candle at the same moment. You see the nearest candles instantly. Farther candles take longer for their light to reach your eyes. The farthest candles might take minutes before you perceive them. But all the candles are already lit. You just haven't seen them yet. The particle horizon is like that. It separates what we've seen from what we haven't seen yet. And the horizon moves. Every second, light from more distant regions reaches us. The observable universe grows larger, not because space is being created, but because light from farther away finally completes its journey. Think of it like a fog lifting. The landscape was always there. You just couldn't see it through the mist. As the fog clears, more terrain becomes visible. Current observations confirm the universe's expansion is accelerating. Dark energy drives this acceleration, and here's where the particle horizon becomes truly strange. In a universe expanding at an accelerating rate, there's a future limit to what we can ever see. Some regions of space are so far away that even though they exist today, their light will never reach us, ever. Expansion will prevent it forever. Two types of horizons exist. The particle horizon marks what we can see now based on the past. The event horizon marks what we can ever see based on the future. And these horizons don't align. They tell different stories about the same universe. The implications make astronomers uncomfortable. Most of the universe is hidden. Most of space exists beyond our reach. And that hidden realm holds secrets we'll never access. What those secrets might be grows more mysterious as we push against the limits. Ask someone how far away a galaxy is and watch them struggle. Distance in an expanding universe is slippery. 3 different answers exist for the same galaxy, and all 3 are correct. This isn't confusion, it's confirmed reality. Take a galaxy at the edge of the observable universe. Its light travel distance is 13.8 billion light-years. That's how long the light has been traveling. Simple enough. But that galaxy has moved since it emitted that light. Today, accounting for expansion, that same galaxy sits 46 billion light-years away. Same galaxy, different distances. Both true. There's a third distance too, co-moving distance. This measures how far the galaxy would be if you froze the universe's expansion right now and stretched a measuring tape through space. It accounts for all the expansion that has occurred and will occur. Cosmologists use co-moving distance because it stays constant as the universe ages. The galaxy doesn't move in co-moving coordinates. Space expands. But the galaxy's position in the cosmic coordinate system remains fixed. Think of drawing dots on a deflated balloon, then inflating it. The dots move apart as the balloon expands, but each dot stays at the same position on the balloon's surface. That position is like co-moving distance. The actual space between dots is like proper distance, and the time it took for light to travel between dots is light travel time. 3 measures, same separation, different meanings. This creates profound confusion about what we mean by location. When we say a galaxy is 46 billion light-years away, we mean that's where it is now according to our best calculations. But we're seeing it as it was 13.8 billion years ago. The galaxy we observe no longer exists in that form. It has evolved. Stars have formed and died. The galaxy might have merged with others. We see ancient history, not present reality. Distance becomes even stranger when we consider galaxies moving away faster than light. These galaxies have recession velocities exceeding 186,000 miles per second. They're not violating relativity. They're not moving through space at that speed. Space itself is expanding between us and them, carrying them away at rates unrestricted by light's speed limit. Observations from the Hubble Space Telescope confirmed this. Galaxies beyond a certain threshold exhibit redshifts, indicating superluminal recession. We can see these galaxies because their light was emitted when they were closer, before expansion accelerated them beyond reach. But any light they emit today will never reach us. Expansion guarantees it. What this means for navigation is unsettling. If you could instantly teleport to a galaxy at the edge of the observable universe, the Earth you left would not be where you expected. Expansion would have carried it billions of light-years from where calculations suggested. You'd arrive at your destination only to find your origin point has vanished into impossible distance. The universe doesn't just expand, it rewrites the meaning of position itself. Every point becomes relative. Every measurement becomes conditional. And at the extremes, the mathematics breaks down into paradox. Yet something exists at those mathematical boundaries, something we can detect. Turn on an old television to a channel with no signal. About 1% of that static is confirmed radiation from the beginning of the universe. The cosmic microwave background, an echo of creation itself, washing over us from every direction in space. 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Before this moment, the cosmos was a hot, dense plasma. Photons scattered constantly off free electrons, unable to travel freely. Light was trapped, the universe was opaque, like trying to see through fog. Then everything changed. Electrons combined with protons to form neutral hydrogen atoms. Suddenly, photons could travel without scattering. Light broke free. The universe became transparent. Those first free photons have been traveling ever since, cooled by expansion into microwaves. They reach us today as the cosmic microwave background, the oldest light we can observe. This radiation comes from a spherical shell around us. Not a physical shell, a shell in time. Every direction you look, you see photons that were released at the same cosmic moment, 380,000 years after the beginning. But because light takes time to travel, nearby photons came from nearby regions, while photons from the opposite side of the sky came from regions billions of light years apart. Measure the temperature of this background radiation and you get 2.7 Kelvin, just 3 degrees above absolute zero. Expansion has stretched the wavelengths, cooling the once hot photons into the microwave range. But measure carefully across the entire sky and you find tiny variations. Some regions are slightly warmer, others slightly cooler. The difference is microscopic, just a few hundred thousandths of a degree. Yet these temperature variations are among the most important discoveries in cosmology. Those variations represent density differences in the early universe. Regions that were slightly denser became seeds for galaxies. Regions that were slightly less dense became voids. The pattern we observe in the cosmic microwave background reveals the blueprint for all cosmic structure. Galaxies, clusters, superclusters, the cosmic web itself, all of it was encoded in those tiny temperature fluctuations. Satellites like WMAP and Planck have mapped the cosmic microwave background with extraordinary precision. Every measurement confirms theoretical predictions. The universe is flat to within less than 1% margin of error. The age matches independent calculations. The composition of matter and energy aligns with other observations. This radiation is a fossil record, a snapshot of the universe when it was just an infant, preserved in light and delivered to us across cosmic time. But here's the unsettling part. We see the cosmic microwave background coming from a distance of 46 billion light-years. That's the particle horizon, the edge of the observable universe. And beyond that edge, the universe continues. More cosmic microwave background exists there, from regions we cannot see. Those photons will never reach us because expansion prevents it. The cosmic microwave background is the ultimate horizon, the farthest thing we can ever observe. But it's not a wall. It's a window showing us the universe's earliest visible moment and reminding us how much remains hidden. What lies just beyond that window defies every assumption about empty space. Special relativity has a famous rule: nothing travels faster than light. Yet, right now, thousands of galaxies are confirmed to be receding from us at speeds exceeding 186,000 miles per second. Some approach twice that speed, others even faster. This isn't science fiction, it's observed reality, and it doesn't break physics. The trick is understanding what moves. In special relativity, objects cannot move through space faster than light. That limit is absolute. But general relativity, Einstein's theory of gravity and spacetime, allows space itself to expand at any rate. There's no speed limit on expansion. Space can stretch faster than light can cross it. Imagine ants on a rubber sheet. Pull the rubber sheet's edges apart rapidly. The ants walk forward at their maximum speed, but the sheet stretches faster than they walk. From the perspective of an ant on one side, ants on the opposite side are moving away faster than any ant can walk. The ants aren't moving faster through the rubber. The rubber itself is expanding, carrying them apart. Galaxies work the same way. They're not racing through space at faster than light speeds. They're embedded in space, and space between us and distant galaxies is expanding rapidly. From our perspective, these galaxies appear to recede faster than light because space carries them away faster than light can cross that expanding distance. Measure the redshift of distant galaxies, and you can calculate their recession velocity. Redshift occurs when light waves stretch due to expansion. The more expansion between emission and reception, the more the wavelengths stretch. Extremely distant galaxies show redshifts, indicating recession velocities many times the speed of light. Yet we can see these galaxies. Why? Because they emitted their light when they were closer. Back then, space between us and them was smaller. The photons traveled toward us, crossing expanding space, gradually approaching despite the recession. Eventually, those photons reached us. But any light those galaxies emit today will never reach us. Expansion has accelerated them beyond a threshold. They've crossed the event horizon. This creates a strange effect. We observe galaxies that are receding faster than light. We see them as they were billions of years ago. But those galaxies are now permanently beyond reach. If we could somehow send a signal to them, traveling at light speed, that signal would never arrive. Expansion would prevent it forever. The galaxies exist. We can see them, but we cannot interact with them, ever. Calculations confirm that galaxies beyond a certain distance, roughly 16 billion light-years in current proper distance, are receding faster than light. That's more than 1/3 of the observable universe. 1/3 of everything we can see is already lost to us. We observe their ancient light, but they're gone, vanished beyond the cosmic horizon. And it gets worse. The universe's expansion is accelerating. Dark energy drives this acceleration. As time progresses, more galaxies will cross the threshold. More regions of space will recede beyond light speed. The observable universe will shrink, not in size, but in accessible content. We'll see light from farther away as time passes, but fewer galaxies will remain within reach. In the distant future, only our local cluster of galaxies will remain visible. Everything else will have been carried away by expansion, vanishing into darkness. Future civilizations will look out and see almost nothing. They'll have no evidence the universe is vast. They'll think they're alone. For now, we can still see, but there are regions of space we cannot pierce no matter how hard we try. Point a telescope at the constellation Centaurus and you'll encounter a problem. The Milky Way galaxy itself blocks your view. Our own galaxy's disk, packed with stars and dust, creates a band of obscuration across the sky. Astronomers call it the zone of avoidance. 10 to 20% of the sky is hidden behind this cosmic barrier, and something massive lurks there. The dust in the Milky Way's galactic plane absorbs visible light. Imagine trying to see through a thick fog. The farther you look, the more the fog obscures. By the time you peer toward the galaxy's center, visible light becomes useless. Billions of stars hide behind dust clouds. Entire regions remain unexplored in optical wavelengths. But astronomers have tricks. Infrared light penetrates dust better than visible light. Radio waves pass through it even more easily. X-ray observations reveal different features. Using these alternate wavelengths, scientists have begun mapping the hidden regions. They discovered something unexpected. The zone of avoidance contains one of the largest concentrations of mass in the nearby universe. Behind the dust, hidden from direct observation, sits the Norma cluster, a massive collection of galaxies, thousands of them, gravitationally bound together, radiating enormous amounts of energy. This cluster was only confirmed in the 1990s because dust made it invisible for so long. Once revealed, it explained something mysterious. In the 1970s, astronomers noticed our galaxy was moving in an unusual direction. not just orbiting the Milky Way's center, not just moving with the expansion of space. The entire local group of galaxies, including the Milky Way and Andromeda, was being pulled toward the constellation Centaurus at 600,000 miles per hour. Something massive was exerting gravitational influence. Something hidden. They called it the Great Attractor, a gravitational anomaly in the zone of avoidance. For years, scientists debated its nature. Was it a supercluster? A concentration of dark matter? Some unknown phenomenon? The dust prevented direct observation. Astronomers could only infer its presence from the motion it caused. Later observations revealed the truth. The Great Attractor is real, but it's not what we thought. The Norma cluster is part of it. But beyond the Norma cluster, even farther into the zone of avoidance, lies something larger, the Laniakea Supercluster, a vast structure containing 100,000 galaxies. The Great Attractor is not a single object, but the gravitational center of this enormous supercluster. Here's what makes the zone of avoidance so frustrating. We know something massive exists there. We can measure its gravitational effects. We can map galaxy movements. But we cannot see it directly in visible light, ever. The Milky Way's dust will always block that view. It's like living in a house with a window painted black. You know something is outside. You hear sounds. You feel vibrations, but you cannot look directly at it. Modern telescopes have partly solved this. Infrared and radio surveys have revealed much of what the dust conceals, but gaps remain. Regions too dense to penetrate even with alternate wavelengths. Areas where uncertainty persists. The zone of avoidance guarantees a blind spot in our cosmic map, a permanent hole in our knowledge. This matters because the structures hidden there are massive. They influence galactic motion across hundreds of millions of light years. Understanding them is crucial to understanding large-scale cosmic structure. Yet we're forced to work with incomplete data, forever denied a full view by our position inside the Milky Way. But hidden structures are not limited to the zone of avoidance. Elsewhere in space, something even stranger exists. Something that shouldn't be possible. In 1981, astronomer Robert Kirshner was mapping galaxy redshifts when he noticed something impossible. A spherical region of space, 330 million light-years across, containing almost nothing. Just 60 galaxies, in a volume that should hold 2,000. The Boötes Void, the largest confirmed empty region in the observable universe. Empty is relative in space. The void isn't a perfect vacuum. It contains some galaxies, but their density is 10% of normal. Imagine a city where 90% of the buildings vanished. That's the Boötes Void, a cosmic ghost town on an incomprehensible scale. 330 million light-years is difficult to comprehend. Light takes 330 million years to cross it. The Milky Way is 100,000 light-years across. You could fit 3,300 Milky Ways side by side across the void. Our entire local group of galaxies, spanning 10 million light-years, would fit into the void 33 times over. This is not a small, empty pocket. This is a gap in the universe's structure. Voids are common. The cosmic web consists of galaxies arranged in filaments and walls surrounding empty spaces. Most voids span 30 to 100 million light-years. They form naturally as gravity pulls matter together into dense regions, leaving emptier spaces between. Scientists understand this process. It's confirmed by computer simulations that match observations perfectly. But the Boötes Void is too large, too empty. Given the universe's age and the way structure forms, a void this big shouldn't exist yet. Gravity hasn't had enough time since the Big Bang to clear out such an enormous region. The mathematics doesn't work, yet there it is, confirmed by multiple surveys and observations. Several theories attempt to explain it. Perhaps smaller voids merged into one supervoid. As galaxies cluster together, the spaces between clusters expand. Over billions of years, adjacent voids could combine. forming larger and larger empty regions. Computer simulations show this is possible, but even accounting for mergers, the Boötes Void seems too big too soon. Another theory involves the cosmic microwave background. Temperature variations in that ancient radiation correspond to density variations in the early universe. Perhaps the Boötes Void originated from an unusually large underdense region 13.8 billion years ago. If so, it's a relic from the universe's infancy, preserved and enlarged by expansion. What makes the void unnerving is its implications. If you lived in a galaxy at the void's center, your night sky would be almost empty. The nearest neighboring galaxy would be tens of millions of light years away. Early astronomers in such a location wouldn't have discovered other galaxies until the 20th century, when telescopes became powerful enough to detect such distant objects. They'd think their galaxy was alone in the universe. Their cosmology would be fundamentally wrong for centuries. We're lucky. The Milky Way sits in a moderately dense region. We have neighboring galaxies. We could discover the universe's true scale. But the Boötes Void reminds us how much luck influences observation. Our cosmic neighborhood shapes what we can learn. A different location would give a different perspective. Neither would be wrong. Both would be incomplete. And the Boötes Void is not alone. Astronomers have discovered other supervoids. The KBC Void, which we might actually be living inside. The Eridanus Supervoid, possibly 500 million light-years across. Each discovery raises the same questions. How did these form? Why are they so empty? What does their existence tell us about the universe's structure? The cosmic web holds more mysteries than most realize, and those mysteries shape our galactic motion in ways we're only beginning to understand. Zoom out far enough and the universe looks like foam. Galaxies cluster into filaments. Filaments intersect at superclusters. Between them, voids. Vast empty regions containing almost nothing. This is the cosmic web, and it's confirmed to be the universe's largest structure. 80% of the observable universe is void. Let that sink in. 4/5 of all space is empty. Galaxies occupy only 1/5 of the volume. Everything we see, every star, every planet, every particle of matter exists in thin threads and clumps surrounded by emptiness. The cosmic web formed through gravity. In the early universe, matter was almost uniformly distributed. Almost. Tiny density variations existed. Regions that were slightly denser had slightly more gravity. They pulled in nearby matter. As they grew denser, their gravity increased. They pulled harder. A feedback loop began. Dense regions became denser. Empty regions became emptier. Over billions of years, this process created filaments. Long streams of galaxies stretching across hundreds of millions of light years. Where filaments intersect, superclusters form. Dense concentrations containing thousands of galaxies. Between filaments, voids expand. Regions where galaxies are rare or absent. Think of soap bubbles. When you blow bubbles in a sink, they cluster together. The soap forms thin walls between bubbles. Most of the volume is air. The cosmic web looks like this. Galaxies form walls and filaments around bubbles of empty space. The bubbles are voids. The walls are where all the action happens. Computer simulations confirm this structure. Scientists input initial conditions based on the cosmic microwave background. They let gravity do its work. The simulations produce a cosmic web matching observations perfectly. Filaments in the right places, voids in the right sizes. The distribution of galaxies aligns with reality. This isn't speculation. This is confirmed understanding. The Sloan Digital Sky Survey mapped a huge volume of space, plotting millions of galaxies. The result was stunning. Clear filamentary structure, obvious voids, the cosmic web revealed in data. Subsequent surveys confirmed and extended these findings. Every new observation reinforces the same picture. The universe, on the largest scales, is a web. But why does this matter? Because structure reveals history. The cosmic web's pattern encodes information about the universe's beginning. The sizes of voids and filaments depend on how matter clumped in the early universe. The distribution of those clumps depends on conditions during inflation. By measuring the web's structure, scientists can test theories about the universe's first moments. Dark matter plays a crucial role. Simulations without dark matter fail to produce the observed web structure. Simulations with dark matter succeed. This is strong evidence that dark matter exists, even though we've never directly detected it. The cosmic web's very existence confirms invisible matter shapes the universe. And the web is dynamic. Galaxies flow along filaments toward superclusters. Voids expand as space stretches. The structure evolves. Billions of years from now, the web will look different. Clusters will merge. Filaments will change. Voids will grow. The universe's architecture is not frozen. It's actively changing. Our galaxy sits on a filament. We're being pulled along that filament toward a dense node. And that node exerts a pull we cannot resist. 600,000 miles per hour. That's how fast the Milky Way is moving toward the constellation Centaurus. Not because we're orbiting anything nearby, because something massive is pulling us. Something that remained hidden for decades. The Great Attractor. In the 1970s, astronomers measured the cosmic microwave background and found an asymmetry. One side of the sky appeared slightly hotter, the other side slightly cooler. This indicated motion. The Milky Way was moving relative to the cosmic microwave background's rest frame. Calculations revealed we're traveling at 600,000 miles per hour in a specific direction. But why? The expansion of the universe doesn't cause this. Hubble expansion is uniform. Every galaxy recedes from every other galaxy equally in all directions. Our motion had to result from gravity. Something massive was pulling us. Something enormous. Astronomers mapped galaxy movements. They found we weren't alone. The Andromeda galaxy is also being pulled. So is the entire Virgo cluster. Hundreds of galaxies are flowing in the same direction, all toward a region behind the zone of avoidance. The hidden gravitational center was named the Great Attractor. For years, the Great Attractor remained mysterious. Dust obscured direct observation. Scientists could only infer its properties from its gravitational effects. Mass estimates suggested it contained tens of thousands of galaxies, but seeing it was impossible in visible light. Infrared and radio telescopes changed everything. They penetrated the dust. Surveys revealed the Norma cluster, a massive concentration of galaxies lying behind the Milky Way's disk. This was part of the Great Attractor, but not all of it. In 2014, astronomers using new mapping techniques discovered something larger, the Laniakea Supercluster, a vast structure containing 100,000 galaxies spread across 500 million light-years. The Great Attractor is the gravitational center of Laniakea. We're part of this supercluster, flowing toward its core like water draining toward a basin. Laniakea means immeasurable heaven in Hawaiian, an appropriate name. The supercluster is almost too large to comprehend. 500 million light-years across, 100,000 galaxies, mass equivalent to 100 million billion times our star, all of it gravitationally connected, flowing together through space. But here's the twist. The Great Attractor isn't the final destination. Beyond Laniakea, even farther away, lies the Shapley Supercluster, an even more massive structure, 650 million light-years distant. Shapley contains tens of thousands of galaxies and exerts gravitational influence across enormous distances. Laniakea itself is being pulled toward Shapley. It's a cosmic cascade. Our galaxy flows toward the Great Attractor. The Great Attractor flows within Laniakea. Laniakea flows toward Shapley, and Shapley might be flowing toward something even larger. The universe on the largest scales is not static. It's a network of flows and currents, gravity pulling structure toward structure in an endless hierarchy. Yet, expansion counteracts this. Dark energy accelerates the universe's expansion. Eventually, expansion will overcome gravity. Laniakea will stop flowing. The structures will freeze in place, then begin separating. Gravity can win temporarily, but expansion wins forever. For now, we're riding a gravitational river, moving through space at speeds we can measure but not feel, heading toward a destination we'll never reach, because the universe's expansion ensures we stay forever within our local neighborhood. The Great Attractor pulls us, but the cosmos itself pulls even harder in the opposite direction. And there's a boundary to this tug of war, a line in space we can see but never touch. 500 million light years. That's the diameter of Laniakea, our home supercluster. To cross it at light speed would take 500 million years. The entire history of complex life on Earth fits into that time span, and we're just a tiny speck within it. Laniakea contains 100,000 galaxies. Each galaxy holds hundreds of billions of stars. Each star might host planets. The numbers become meaningless. Billions of billions of billions of objects, all gravitationally connected, all part of one enormous structure flowing through space together. The supercluster is not a fixed object. It's a region of space where galaxy movements converge. Think of a watershed. Rain falls on mountains. Water flows downhill toward rivers. Rivers merge into larger rivers. All the water eventually flows toward the lowest point. Laniakea works the same way. Galaxies flow along paths determined by gravity, converging toward the Great Attractor at the supercluster's center. Mapping Laniakea required a breakthrough. Astronomers couldn't just measure galaxy positions. They needed to measure galaxy velocities, how fast each galaxy was moving, in what direction. This revealed the flow patterns. By tracing those flows backward, scientists identified the boundaries where flows from different superclusters meet. Picture water flowing from different watersheds. At the ridge between watersheds, water flows in opposite directions. One side drains toward one river system. The other side drains toward a different system. The ridge marks the boundary. Laniakea's boundaries work the same way. They're the ridges in the cosmic flow where galaxy movements diverge. This means superclusters are not discrete objects with hard edges. They're regions defined by gravitational flow. The boundaries are gradual transitions, not walls. But the concept is useful. It allows us to map the universe's structure in a meaningful way. Laniakea is not alone. Other superclusters exist. The Perseus-Pisces supercluster, the Coma supercluster, the Shapley supercluster. Each contains tens of thousands to hundreds of thousands of galaxies. Each spans hundreds of millions of light years, and they're separated by voids even larger. But here's what's unsettling. Laniakea is not gravitationally bound. Dark energy's acceleration ensures that. The supercluster's components flow together now, pulled by gravity. But expansion is winning. Eventually, the flows will stop. Galaxies will freeze at their current positions relative to each other. Then expansion will tear the supercluster apart. In 1 trillion years, Laniakea won't exist. The galaxies will have separated beyond any meaningful connection. Future astronomers in the Milky Way will look out and see only the local group, maybe a few dozen nearby galaxies. Everything else will have vanished beyond the cosmic horizon, carried away by expansion into permanent isolation. For now, Laniakea is our neighborhood, our cosmic address. We live in the Milky Way galaxy, in the local group of galaxies, near the Virgo cluster, within the Laniakea supercluster. This structure defines our local universe. It shapes galactic motion. It creates the gravitational landscape we navigate. But Laniakea is just one supercluster among many. The observable universe contains millions of superclusters. Each one is a system of flows and structures. Each one will eventually disintegrate as expansion wins. The cosmic web is temporary. Gravity assembles it. Dark energy will disassemble it. And some of that web is already beyond reach, locked behind a barrier we'll never cross. Right now, 16 billion light years away, there's a galaxy emitting light toward us. That light will never arrive. Ever. Not in a trillion years. Not in a Google years. Never. Because the space between us and that galaxy is expanding faster than the light can cross it. This is the cosmic event horizon. The event horizon is not the same as the particle horizon. The particle horizon marks what we can see based on the past, light that has already reached us. The event horizon marks what we can ever see based on the future, light that will reach us eventually versus light that will never reach us. In a universe with constant or decelerating expansion, the event horizon would be infinite. Given enough time, light from any distance would eventually reach us. But our universe is accelerating. Dark energy drives this acceleration, and acceleration creates an event horizon, a boundary beyond which light emitted now can never reach us. Calculate the event horizon's current location, and you get 16 billion light-years. Galaxies closer than this threshold can still send light that will eventually reach us. Galaxies farther than this threshold cannot. Any photons they emit today will be carried away by expansion faster than they approach us. The photons travel toward us at light speed, but the space between us expands faster. The photons lose ground. They never arrive. Think of a treadmill. You walk forward at 3 miles per hour, but the treadmill moves backward at 4 miles per hour. You walk. You make progress relative to the treadmill belt, but you move backward relative to the room. You never reach the front of the treadmill. Light from beyond the event horizon faces the same problem. It travels toward us, but expansion carries it backward faster than it advances. This creates a bizarre situation. We can see galaxies beyond the event horizon. We observe them as they were billions of years ago. Their ancient light reached us. But those same galaxies today are beyond the threshold. We cannot see their present state. We never will. We're looking at ghosts. Images of galaxies that exist but are now forever disconnected from us. Here's where it gets stranger. The event horizon is shrinking in co-moving coordinates. As acceleration continues, more regions of space cross the threshold. Galaxies that today can still send light to us will tomorrow be unable to do so. The universe is erasing itself from our view, not because galaxies are being destroyed, because expansion is carrying them beyond reach. In the far future, trillions of years from now, the event horizon will have shrunk to encompass only our local group of galaxies. Everything else will have crossed the boundary. Future civilizations will look out and see almost nothing. The night sky will be mostly empty. The cosmic microwave background will have redshifted into invisibility. They'll have no evidence the universe is vast. No evidence of the Big Bang. No evidence of other galaxies. Their astronomy will be fundamentally limited. We live in a privileged time. We can still see most of the cosmic web. We can observe distant galaxies. We can detect the cosmic microwave background. We can study the universe's history. But this window is closing. Slowly, inevitably. The universe is disappearing from view. And the event horizon is just one type of boundary. The observable universe itself is determined by light's travel time, not by physical barriers. But there are boundaries of another kind, boundaries imposed by the universe's geometry. Draw a triangle in space, measure its angles, add them up. If you get exactly 180 degrees, the universe is flat. If you get more, the universe is closed. If you get less, the universe is open. This simple test determines everything about the universe's fate. A flat universe has zero curvature, like a sheet of paper extended infinitely in all directions. Parallel lines remain parallel forever. Triangles follow Euclidean geometry. This is the shape most cosmological models predict, and it's what observations confirm. A closed universe has positive curvature. Like the surface of a sphere, parallel lines eventually meet. Triangles have angles adding up to more than 180 degrees. A closed universe is finite in size. Traveling far enough in a straight line would bring you back to your starting point, like walking around Earth's surface. An open universe has negative curvature. Like the surface of a saddle, parallel lines diverge. triangles have angles adding up to less than 180 degrees. An open universe is infinite. Traveling forever in a straight line would never bring you back. You'd encounter endless new regions. Measure the universe's geometry, and you measure its density. The critical density is 6 hydrogen atoms per cubic meter. If the average density equals this, the universe is flat. If density exceeds this, the universe is closed. If density is less, the universe is open. Observations from satellites measuring the cosmic microwave background have determined the geometry. The Wilkinson Microwave Anisotropy Probe, the Planck satellite, both found the universe is flat to within a fraction of a percent. The density equals the critical density. Space has no detectable curvature. This has profound implications. A flat universe is either infinite or finite but unbounded. If infinite, space extends forever in all directions. Countless galaxies exist beyond what we can observe. An endless expanse. If finite but unbounded, space curves back on itself in higher dimensions, like a torus. You could travel forever without hitting an edge, yet eventually return to your starting point. Current observations cannot distinguish between infinite and finite, but unbounded. Both are consistent with flatness. The universe could be infinite, or it could be huge, but closed. We cannot tell. The observable universe is too small a sample to determine the universe's global topology. Flatness also determines the universe's fate. In a flat universe dominated by dark energy, expansion accelerates forever. Galaxies separate. Stars exhaust their fuel. New star formation ceases. Eventually, the universe becomes cold, dark, and empty. This is called heat death, the slow dissolution of all structure. A closed universe might recollapse. Gravity could eventually overcome expansion, pulling everything back together in a big crunch. But our universe doesn't appear to be closed. Dark energy prevents recollapse. An open universe also expands forever. Like a flat universe, it ends in heat death. The geometry determines what's possible, but dark energy determines what actually happens. What's bizarre is how precisely the universe balances at flatness. Slightly more density, and it would be closed. Slightly less, and it would be open. The fact that we measure exactly critical density suggests something about the universe's initial conditions. Inflation theory predicts flatness. The rapid expansion in the first fraction of a second after the Big Bang would have stretched any curvature to imperceptibility. The universe looks flat because inflation made it flat. But flatness is just one property. The universe's contents matter equally, and those contents include something we don't understand. 6 hydrogen atoms per cubic meter. That's all it takes. The difference between a universe that expands forever and one that collapses back on itself, the critical density, a razor's edge separating infinite from finite futures. Calculate the universe's actual density, and you get numbers matching the critical density almost exactly. Too close to be coincidence. The universe sits balanced at the threshold. Why? Nobody knows. It's one of cosmology's deepest mysteries. Density determines curvature. High density means lots of matter. Lots of matter means strong gravity. Strong gravity curves space positively, creating a closed universe. Low density means weak gravity. Weak gravity allows space to curve negatively, creating an open universe. Critical density is the boundary, just enough matter to balance expansion and gravity perfectly, creating a flat universe. Observations confirm the universe contains approximately 5 atoms per cubic meter, mostly hydrogen, some helium, trace amounts of heavier elements. This is ordinary matter, the stuff stars and planets are made from. It accounts for about 5% of the critical density, but there's more. Dark matter contributes about 27%. Dark matter is invisible. It doesn't emit or absorb light. We detect it only through its gravitational effects. Galaxy rotation curves, gravitational lensing, cluster dynamics, all confirm dark matter exists. Yet we've never directly observed a dark matter particle. we don't know what it's made of. Together, ordinary matter and dark matter total 32%, still short of critical density. The remaining 68% is dark energy, an unknown form of energy causing the universe's expansion to accelerate. Dark energy has negative pressure. It pushes space apart rather than pulling it together. Nobody knows what dark energy is. We just know it exists because expansion is accelerating. Add up the components: 5% ordinary matter, 27% dark matter, 68% dark energy. Total, 100% of critical density. The universe is exactly balanced at flatness. This is deeply puzzling. Why should the universe's contents add up to precisely critical density? Why not 90% or 110%? The fact that we measure exactly 100% suggests something fundamental we don't understand. One possible explanation is inflation. During the universe's first fraction of a second, space expanded exponentially. This rapid expansion would have flattened any initial curvature. It would have driven the density toward critical, regardless of initial conditions. Inflation predicts flatness, and we observe flatness. This is strong evidence inflation occurred. But inflation doesn't explain dark energy. Why does the universe contain exactly the right amount of dark energy to maintain critical density? Is this a coincidence? Or does some mechanism we don't understand keep the density balanced? Another mystery: dark energy's strength. If dark energy was slightly stronger, expansion would have accelerated so rapidly that galaxies never formed. If slightly weaker, the universe might have recollapsed before stars ignited. The value seems fine-tuned, too fine-tuned. This suggests either extraordinary luck or unknown physics. Some scientists propose the anthropic principle. We observe this universe because we exist in it. If constants were different, we wouldn't be here to observe anything. Only universes with the right properties allow life, so it's no surprise we find ourselves in one. But this explanation is unsatisfying. It doesn't explain why the constants have the values they do. It just says we couldn't exist otherwise. The critical density mystery remains unsolved. We measure flatness. We measure critical density. We don't understand why. The universe balances on a knife edge, and nobody knows what holds it there. Meanwhile, that balance creates geometry with specific properties that determine what parallel lines do in four-dimensional space. In flat space, parallel lines remain parallel forever. Draw two straight lines that never touch. Extend them infinitely. They never converge, never diverge. This is Euclidean geometry. The geometry you learned in school, and it's confirmed to be the universe's geometry. But understanding flatness in 4 dimensions is difficult. We live in 3 spatial dimensions plus time. Our brains visualize 3 dimensions easily. 4 is harder. Yet the universe's geometry is 4-dimensional. Space and time curve together. Grasping this requires analogies. Imagine a 2-dimensional creature living on a sheet of paper. The paper is flat. Parallel lines drawn on it never meet. The creature could measure triangle angles and find they sum to 180 degrees. The creature would conclude its universe is flat. Now extend this to 3 dimensions. We live in 3-dimensional space. If our space is flat, parallel lines in any direction remain parallel. Triangles obey Euclidean rules. Measurements confirm this is true. But add time as a 4th dimension. Space and time interweave into space-time. Einstein's general relativity describes how mass and energy curve space-time. Yet the overall curvature, averaged across the universe, is 0. Space-time as a whole is flat. This has consequences. In curved space, geometry changes. On a sphere, 2 lines starting parallel eventually meet. Draw 2 lines from Earth's equator toward the North Pole. They begin parallel, but they converge and cross at the pole. Spherical geometry doesn't match Euclidean rules. On a saddle surface, parallel lines diverge. Start 2 lines parallel. They spread apart as you extend them. Saddle geometry is non-Euclidean in the opposite direction from spherical geometry. Flat geometry is special. It's the boundary case, the transition between positive and negative curvature, and our universe sits exactly at that boundary. Measurements show curvature is 0 to within less than 0.5% error. Either the universe is exactly flat, or it's so close we cannot tell the difference. Why does this matter? Because flatness determines infinity. A flat universe is either infinite or finite with special topology. If infinite, space extends forever. Endless galaxies, endless stars, endless everything. If finite, space wraps around itself in higher dimensions. Traveling far enough brings you back to the starting point, but there's still no edge, no boundary, no wall. Current observations cannot distinguish between these possibilities. The observable universe is too small. If the universe wraps around itself, the wrapping occurs on scales larger than we can observe. We might live in a finite universe and never know it, but whether infinite or finite, flat geometry guarantees certain properties. Light travels in straight lines unless deflected by mass. Distances add linearly. Volumes scale as the cube of linear dimensions. These are the rules of Euclidean space, extended to cosmic scales. And these rules make predictions we can test. Measure angles in the cosmic microwave background. Compare them to theoretical predictions. If the universe is flat, specific patterns should appear. Observations confirm those patterns. The universe passes the test. Flatness is real. Yet flatness alone doesn't tell the whole story. The universe is not just flat, it's expanding, and that expansion is accelerating. The combination of flatness and acceleration creates a scenario unlike anything imagined before dark energy's discovery. What that scenario means for the universe's future is more unsettling than most people realize. 1998 changed everything. Two teams of astronomers were measuring distant supernovae, expecting to find the universe's expansion slowing down. Gravity should decelerate expansion, pull galaxies closer together, eventually stop expansion entirely. That was the prediction. The measurements showed the opposite. Expansion is accelerating, getting faster. Something is pushing the universe apart. They called it dark energy. Nobody knows what it is. We just know it exists because we measure its effects. Dark energy has negative pressure. Instead of pulling, it pushes. Instead of attracting, it repels. It's the opposite of gravity in every way except one. Both affect spacetime itself. Dark energy makes up 68% of the universe's total energy content. More than matter, more than dark matter, more than radiation. It dominates everything, and its strength appears constant. Every cubic meter of space contains the same amount of dark energy. As space expands, more space is created. More space means more dark energy. More dark energy means stronger acceleration. This creates a runaway effect. Expansion accelerates. Acceleration creates more space. More space contains more dark energy. More dark energy accelerates expansion faster. The cycle feeds itself. Forever. Calculate the future, and you get a universe that never stops expanding. Galaxies separate at increasing rates. First, distant galaxy clusters vanish beyond the cosmic horizon. Then nearby clusters. Eventually, only our local group remains visible. In trillions of years, even Andromeda might be too far away to see clearly after we merge with it. But it gets worse. Dark energy might not stay constant. Some theories suggest it could strengthen over time. If that happens, acceleration becomes extreme. Eventually, expansion grows so rapid it tears apart galaxy clusters, then galaxies themselves, then star systems, then planets, then molecules, then atoms. This scenario is called the Big Rip. The universe literally rips itself apart at the seams. Other theories suggest dark energy might weaken. If so, matter's gravity could eventually overcome it. Expansion might reverse. The universe could begin contracting, ending in a big crunch. All matter compressed back into a singularity. Everything that exists crushed into infinite density. But current observations show dark energy's strength remaining constant, year after year, measurement after measurement. The cosmological constant, a fixed energy density in every cubic meter of space. This leads to heat death. Expansion continues forever. Galaxies separate, stars burn out, black holes evaporate. Eventually, the universe becomes cold, dark, and empty. Particles separated by incomprehensible distances, nothing interacting with anything else. The acceleration we observe today is relatively gentle. Galaxies beyond a certain distance recede faster than light, but nearby galaxies remain gravitationally bound. The Milky Way and Andromeda will still collide in a few billion years. Gravity wins locally. Dark energy wins globally. Yet the boundary between these realms is shrinking. More galaxies cross the event horizon every moment. More regions vanish from view. The universe is erasing its own history, removing evidence of its structure, leaving future observers with an incomplete picture of reality. And this erasure is already happening. Galaxies we can see today are already gone, in a sense. Look at the Hubble Deep Field. Thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length. Every spot of light is a galaxy containing billions of stars. Many of these galaxies are over 13 billion light-years away. We see them as they were when the universe was young, infant galaxies forming their first stars. But here's the disturbing truth. Many of those galaxies no longer exist in observable form. They've crossed the cosmic event horizon. The light we receive left them billions of years ago when they were closer. Since then, expansion has carried them beyond the boundary. Any light they emit today will never reach us. We're looking at ghosts, historical records of galaxies that are now permanently disconnected. They still exist somewhere in space, but they might as well be in another universe. No information exchange is possible. No observation, no interaction. They're gone. Calculations confirm this. Galaxies with redshifts above a certain threshold have recession velocities exceeding light speed. They're moving away faster than light can cross the expanding space between us and them. We can see their past. We cannot see their present or future. Count the galaxies in the observable universe and you get approximately 2 trillion. But count how many are actually within reach, meaning we could theoretically send a signal they would receive, and the number drops dramatically. Most galaxies we observe are already beyond the event horizon. We're seeing their ancient light, but they're lost to us forever. This creates a strange form of cosmic archaeology. Every deep field image from telescopes is a historical document, a snapshot of the universe as it was, not as it is. The farther we look, the farther back in time we see. The farthest galaxies we observe existed over 13 billion years ago. They're seeing light that left shortly after the Big Bang. Those galaxies today are over 46 billion light-years away, far beyond any hope of contact. And the situation worsens every second. Acceleration continues. The event horizon shrinks in co-moving coordinates. Galaxies that today are just barely within reach will tomorrow be beyond it. The universe is a shrinking island of accessibility in an ocean of disconnection. Picture a boat drifting away from shore while you swim after it. You swim at maximum speed, but the current pushes the boat faster than you can swim. You get tired. The boat vanishes over the horizon. You never catch it. That's light from distant galaxies, traveling at maximum speed. But expansion creates a current too strong. The galaxies vanish forever. Some astronomers find this depressing. The universe is vast, but most of it is locked away. We'll never explore it, never study it, never understand what's happening in those disconnected regions. Future civilizations will have even less access. They'll wonder if anything exists beyond their local group. They'll have no way to find out. But there's another perspective. We live in a special time. We can still see most of the cosmic web. We can observe the universe's structure. We can study distant galaxies. We can detect the cosmic microwave background. This window of observation is temporary. Someday it will close, but for now, it's open. We have the privilege of seeing the universe while it's still visible. Every photograph from Hubble, every measurement from Planck, every observation from ground-based telescopes is a gift, a glimpse of the cosmos before acceleration hides it. We're living in the universe's youth, when structure is still forming, when galaxies are still accessible, when the cosmic microwave background is still detectable. In 1 trillion years, none of this will be true. But there's a boundary even closer than the event horizon, a threshold that defines what we'll ever reach. 16 billion light-years. That's the cosmic event horizon's current location. Galaxies closer than this can still send light that will eventually reach us. Galaxies farther cannot. This boundary moves. It changes as the universe expands, but it always exists, and it's always final. The event horizon is defined by future light cones. In relativity, every point in spacetime has a light cone, the set of all events that can affect it or be affected by it. For events outside your light cone, no causal connection is possible. No signal, no information, nothing. Extend this concept to cosmology. Earth has a future light cone, the set of all events we can potentially observe in the future. That cone has a boundary, the cosmic event horizon. Events beyond this boundary are forever outside our light cone. We'll never see them, never know about them, never interact with them. What makes this boundary interesting is that we can see beyond it. We observe galaxies that are now past the event horizon. Their ancient light reached us, but their current state is hidden. We're seeing history without seeing the present. Calculate the event horizon precisely, and you need to know dark energy's behavior. If dark energy remains constant, the event horizon sits at about 16 billion light-years in proper distance. If dark energy strengthens, the horizon moves closer. If it weakens, the horizon moves farther away. Current observations suggest constancy, the cosmological constant model. But uncertainty remains. Here's what's verified. Galaxies we observe at high redshifts are beyond the event horizon. Their light left them when they were closer. Expansion carried them beyond the threshold while their light was in transit. We're seeing them before they crossed. We're missing everything that happened after. Think of a friend moving away on a train. You watch them go. They wave. You wave back. Eventually, the train curves around a mountain. Your friend disappears from view. You know they're still on the train, still traveling, but you can't see them anymore. The cosmic event horizon is like that mountain. Galaxies curve beyond it. They're still there, but they vanish from view, and unlike the train, they're never coming back. The train might return, the galaxy won't. Expansion ensures permanent separation. This has profound implications for cosmic destiny. Most of the universe will eventually be beyond our event horizon, not beyond our particle horizon, which marks what we can currently see. Beyond our event horizon, which marks what we can ever see. The difference matters. The particle horizon grows as light from farther away reaches us. The event horizon shrinks as acceleration carries more regions beyond reach. In the far future, these horizons converge. The particle horizon stops growing. It settles at a maximum size. Everything beyond that maximum is permanently invisible. Future observers will see a small, static universe. A few thousand galaxies in their local group. Nothing else. No cosmic microwave background. No distant quasars. No evidence of the Big Bang. Their cosmology will be fundamentally limited by accident of timing. We're luckier. We can still observe the universe's true structure. But this privilege is temporary. The window is closing, not on human timescales, but on cosmic timescales. Billions of years from now, the view will be very different. Yet even now, the universe has hard limits, limits imposed by something more fundamental than expansion. The universe is 13.8 billion years old. That's a hard limit. Nothing we observe is older. Nothing can be. Light from the cosmic microwave background has been traveling for 13.8 billion years. It shows us the universe as it was 380,000 years after the beginning. Before that, the universe was opaque. No light could travel freely. We have no direct observations of earlier times. This creates a boundary in time, not space. The observable universe is limited by age. Light needs time to travel. The farther away something is, the longer its light takes to reach us. At some distance, the light hasn't had time to arrive yet. Beyond that distance, we see nothing. Not because nothing exists there, because their light hasn't reached us. Think of it like news traveling by horseback. A rider leaves a distant city carrying a message. The rider travels at maximum speed, but if the city is far enough away, the rider hasn't arrived yet. The message exists. The city exists. You just haven't received the news. The cosmic microwave background is like that rider. It's been traveling since the universe became transparent. It's still arriving. We receive it now, but photons from more distant regions are still in transit. As time passes, the observable universe grows. Not because space is created, because light from farther away finally reaches us. Every second, photons arrive that have been traveling for billions of years. They expand our view. We see farther, we see earlier. But there's always a limit based on age. This means the early universe is hidden from us. We see the cosmic microwave background from 380,000 years after the Big Bang. We cannot see earlier directly. The universe before that time was too hot and dense. Photons scattered constantly. They couldn't travel freely. The cosmos was foggy. Scientists have other ways to study earlier times. Neutrinos from 1 second after the Big Bang could theoretically be detected, though we haven't yet. Gravitational waves from cosmic inflation might leave imprints in the cosmic microwave background. We can infer early conditions from the structure we observe today, but direct observation of the first 380,000 years remains impossible with light. The Big Bang itself is beyond observation, not just beyond current technology, beyond possibility. The moment of creation left no photons we can detect. Everything was too hot, too dense. Physics breaks down at those conditions. Our equations stop working. We have theories, we have models, but we have no direct evidence. This creates an ultimate horizon, a boundary in time before which observation becomes impossible. We can theorize about the first fraction of a second. We can model inflation. We can calculate quantum fluctuations, but we cannot observe them directly. We're separated from the universe's beginning by an impassable barrier of time and physics. Yet, within the observable universe, within the region whose light has had time to reach us, there are zones of rapid motion, regions where something invisible exerts enormous influence. Imagine a sphere around Earth, where galaxies at that distance recede at exactly light speed. Inside the sphere, recession velocities are slower than light. Outside the sphere, faster. This sphere is called the Hubble sphere, and it's one of the most misunderstood concepts in cosmology. Many people think the Hubble sphere is the edge of the observable universe. It's not. We can see beyond it. We observe galaxies receding faster than light. The Hubble sphere marks recession velocity, not observability. It's a kinematic boundary, not an observational one. Calculate the Hubble sphere's radius and you get about 14 billion light-years in proper distance. At this distance, the recession velocity equals light speed. Closer galaxies recede slower. Farther galaxies recede faster. This is confirmed by redshift measurements. The relationship is linear at moderate distances. Redshift increases with distance. Velocity increases with distance. At some point, velocity crosses the light speed threshold. But crossing this threshold doesn't make galaxies invisible. We can observe galaxies well beyond the Hubble sphere. Their light reaches us because they emitted it when they were inside the sphere. Back then, they were closer. Their light could make progress toward us. Over billions of years, that light crossed expanding space and eventually arrived. By the time it reached us, the source galaxy had moved beyond the Hubble sphere. But we still see the light. Think of running on an airport moving walkway that goes the wrong direction. You run forward at 5 miles per hour. The walkway moves backward at 3 miles per hour. Your net speed is 2 miles per hour forward. You make progress. Eventually, you reach the end. Now imagine the walkway accelerates to 7 miles per hour backward. You run at 5 forward, but you move backward at 2 overall. You lose ground. That's a galaxy beyond the Hubble sphere. It emits light toward us, but expansion carries it backward faster than the light approaches. However, if the light was emitted before the galaxy crossed the Hubble sphere, it might still reach us eventually. The photons were already inside, already making progress. They continue forward. The source recedes, but the photons keep traveling. Some make it, some don't. It depends on when they were emitted and how fast expansion accelerates. The Hubble sphere is not fixed. It changes as the expansion rate changes. If expansion accelerates, the Hubble sphere shrinks in co-moving coordinates. More galaxies cross outward. They move from recession velocities below light speed to above light speed. If expansion decelerates, the sphere grows. Galaxies that were receding faster than light might slow down below the threshold. In our universe, dark energy causes acceleration. The Hubble sphere's size in co-moving distance shrinks over time. More and more galaxies cross outward. First, the most distant ones. Eventually, closer ones. In the far future, even nearby galaxy clusters might cross the Hubble sphere, receding faster than light. But remember, crossing the Hubble sphere doesn't equal invisibility. The event horizon determines that. The Hubble sphere is just a convenient marker, a way to visualize recession velocities. It's useful for calculations, but it's often confused with other horizons. That confusion misleads people into thinking we can't see galaxies receding faster than light. We can. We do. Observations confirm it. What matters more is how much of the universe remains accessible, how much is already lost. Count all the galaxies in the observable universe. About 2 trillion. Now count how many we could theoretically reach with a signal traveling at light speed. Far fewer. Most galaxies we observe are beyond the event horizon. We can see them because their light left billions of years ago, but we cannot send signals they would ever receive. Estimates vary, but most calculations suggest around 78% of galaxies in the observable universe are already beyond our causal reach. They're too far. Expansion has carried them beyond the event horizon. Any signal we send, traveling at light speed, will never reach them. It will be carried backward by expansion faster than it advances. 22% remain within reach. Galaxies in our local supercluster mostly. Some nearby galaxy groups. These are gravitationally connected to us. They're not being carried away by expansion. Or, at least, expansion is weak enough that gravity dominates. We could theoretically send signals. They would arrive, eventually, but that 22% is shrinking. Acceleration continues. The event horizon draws closer in co-moving coordinates. Galaxies at the edge of reachability cross the threshold. They transition from accessible to inaccessible. The universe contracts around us, not physically, causally. This means most of the universe is forever beyond contact. We can observe it, we cannot interact with it. It's like watching a movie. You see the characters, you hear the dialogue, but you cannot affect the plot, cannot change outcomes, cannot communicate. You're a passive observer of events you cannot influence. Some scientists find this philosophically troubling. What does it mean to exist if most of existence is unreachable? Does the unreachable universe matter? Can we claim to understand the cosmos when we're locked away from most of it? Others argue we should be grateful. 22% of 2 trillion galaxies is still hundreds of billions of galaxies, an incomprehensible number of star systems, countless planets. If intelligence exists elsewhere, it likely exists within our causal reach. We're not completely isolated, just mostly isolated. But the long-term trend is clear. Accessible regions shrink. In 1 trillion years, maybe only our local group remains within reach. In 100 trillion years, even that might be questionable. If dark energy strengthens, isolation could come faster. The universe could fragment into disconnected bubbles, each bubble seeing only itself. No evidence others exist. Current observations show dark energy remaining constant, the cosmological constant. If that continues, we're headed for a future of profound isolation. Our descendants, billions of years from now, will inhabit a galaxy cluster alone in an empty, expanding cosmos. They'll see no other galaxies, no cosmic microwave background, no evidence of the universe's youth. Their cosmology will be stunted by timing. We live in the age of visibility. The universe is still young enough to be observed. Structure is still forming. Light from distant regions still reaches us. This window won't last forever. It's already closing. 78% is already gone. The remaining 22% is dwindling. Yet the greatest mystery is not what we've lost. It's what might exist beyond everything we could ever hope to reach. The observable universe is finite, 92 billion light-years across. But the universe itself might be infinite, extending forever in all directions. Endless space, endless galaxies, endless everything. Or it might be finite but unbounded, huge but closed, like a higher dimensional sphere. Either way, it's larger than we can observe. Measure the universe's curvature and you get zero. Flat space, no curvature. This means the universe is either infinite or so large its curvature is undetectable. Current observations cannot distinguish between these possibilities. Both are consistent with flatness. An infinite universe is difficult to comprehend. Imagine traveling in a straight line forever. You never reach an edge, never encounter a boundary. Space continues, galaxies continue, structure continues, forever. There's no center. Every point is equivalent. Every observer sees themselves surrounded by approximately the same density of galaxies. In an infinite universe, everything that can happen does happen. Somewhere, if the universe is infinite and matter is distributed uniformly on large scales, then every possible configuration of atoms exists somewhere. Every possible planet, every possible life form, every possible history. There are infinite copies of Earth, infinite copies of you, existing in regions so distant you could never observe them or interact with them. This idea disturbs some people. It suggests nothing is unique. Everything repeats infinitely, but the distances involved are incomprehensible. The nearest identical copy of you might be 10 to the power of 10 to the power of 30 meters away, a number so large it has no practical meaning. You'll never meet your doppelganger. The universe is too vast. Alternatively, the universe might be finite but unbounded, like a three-dimensional surface of a four-dimensional sphere, or a torus, or some other topology. You could travel forever without hitting an edge. Eventually, you'd return to your starting point. But the journey would take longer than the universe's current age. Much longer, trillions of years, maybe more. If the universe has this topology, we might detect it. Light traveling around the universe could create multiple images of the same galaxy in different directions. Astronomers have searched for such patterns. They found nothing. If the universe loops back on itself, the loop is larger than the observable universe. We're too small to detect it. Some cosmologists favor infinity. Inflation theory predicts it. The rapid expansion in the universe's first moments would have stretched any initial curvature to imperceptibility. If inflation lasted long enough, it created an effectively infinite universe, small patches inflated to cosmic scales. Our observable universe is just one patch among infinite patches. Other cosmologists are agnostic. We cannot measure beyond the observable universe. We cannot verify infinity. It remains a theoretical possibility. not an observational fact. Philosophically, it's interesting. Scientifically, it's untestable. We'll never know for certain unless we find some indirect evidence. What we do know is this: the universe is vast beyond comprehension. Whether infinite or merely enormous doesn't change our cosmic insignificance. We inhabit a tiny region of space. We observe a tiny fraction of what exists. Everything beyond our horizon continues whether we see it or not, and some scientists believe our universe itself might be just one among many. Inflation theory solves many cosmological problems. It explains why the universe is flat, why it's uniform, why distant regions have the same temperature despite never being in causal contact. But inflation comes with a consequence. If it happened once, it's probably still happening, somewhere. Eternal inflation is the idea that inflation never completely stops. It ends in some regions, creating bubble universes. Our observable universe is one bubble, but beyond our bubble, space continues inflating. And that inflating space occasionally spawns new bubbles. Each bubble is a universe. Each universe has its own properties, different physical constants, different laws, different structures. This is the multiverse, an infinite ensemble of bubble universes embedded in eternally inflating space. Some bubbles are similar to ours. Some are radically different. Some allow galaxies and stars. Some don't. Some support life. Some are sterile. Every possibility is realized somewhere in the infinite multiverse. Evidence for the multiverse is indirect. We observe our universe is flat, uniform, structured. These properties require fine-tuning. If physical constants were slightly different, galaxies wouldn't form, stars wouldn't ignite, life couldn't exist. The fact that we observe a life-permitting universe seems improbable. Unless many universes exist with different constants, then we simply find ourselves in one where life is possible. Anthropic selection. Another hint comes from quantum mechanics. The many worlds interpretation suggests the universe splits every time a quantum measurement occurs. Each outcome exists in a separate branch. This creates a multiverse of quantum possibilities, not the same as eternal inflation's multiverse, but conceptually similar. Multiple realities existing simultaneously. String theory also predicts a multiverse. The theory allows enormous numbers of possible vacuum states. Each state corresponds to different physics, different particle masses, different force strengths. If all these vacua are realized somewhere, we have a landscape of universes. Ours is just one point in that landscape. But here's the problem. The multiverse might be untestable. If other universes are beyond our observable horizon, we cannot observe them, cannot measure them, cannot verify they exist. They're forever disconnected from us. Any theory predicting them becomes unfalsifiable. Science requires testability. If a theory makes no testable predictions, is it science? Some physicists embrace the multiverse enthusiastically. They see it as a natural consequence of well-established theories like inflation. Others reject it as speculation. They demand empirical evidence. They argue that invoking infinite, unobservable universes to explain one observable universe is not scientific reasoning. The debate continues, but what's clear is this. If the multiverse exists, our universe is infinitesimally small within it. One bubble among infinite bubbles. One set of physical laws among infinite possibilities. Our entire cosmic history, from Big Bang to heat death, is just a brief fluctuation in one corner of a vastly larger structure. This idea humbles. Our galaxy is tiny. Our observable universe is tiny. But if the multiverse exists, even our universe is tiny. We're nested layers of insignificance. A planet in a star system, in a galaxy, in a supercluster, in an observable universe, in a bubble universe, in an eternally inflating multiverse. Each layer reduces our cosmic importance. Yet, we exist, we observe, we think, we question, and our small corner of reality contains enough mystery to occupy us forever, including mysteries written into the cosmic microwave background itself. Scan the cosmic microwave background, and you find tiny temperature variations. Regions slightly warmer, regions slightly cooler. These variations are seeds for cosmic structure. Denser regions became galaxies. Underdense regions became voids. The pattern is confirmed to match predictions perfectly, except for one feature, the cold spot. In the constellation Eridanus, there's a region about 10 degrees across that's significantly colder than surrounding areas. Not just a little colder, much colder. About 70 microkelvins below average. This is far larger and colder than typical fluctuations. Statistical analysis confirms it shouldn't exist. The probability of such a feature arising randomly is less than 1%. When astronomers first detected the cold spot in 2003, they assumed it was an error, instrumentation problem, data processing glitch. But subsequent observations from different satellites confirmed it. The cold spot is real. It exists in the cosmic microwave background, and nobody knows why. Several theories attempt to explain it. One possibility is a supervoid, an enormous empty region of space between us and the cosmic microwave background. Photons traveling through such a void would lose energy to expansion, arriving slightly cooler. This is the integrated Sachs-Wolf effect. If a supervoid large enough existed in the right location, it might create the cold spot. Surveys searched for such a supervoid. They found suggestions of underdense regions aligned with the cold spot, but nothing definitively large enough to explain the temperature anomaly. The evidence remains ambiguous. Maybe a supervoid exists. Maybe it's smaller than needed and combined with other effects. Maybe it's not there at all. Another theory suggests cosmic textures. Defects in spacetime left over from phase transitions in the early universe. These textures could create temperature anomalies in the cosmic microwave background. The cold spot might be evidence of such a defect, but cosmic textures are speculative. We've never confirmed they exist. More exotic theories invoke parallel universes. If bubble universes collided in the early universe, they might leave imprints on the cosmic microwave background. Cold spots could mark collision points. This sounds like science fiction. But some physicists take it seriously. Eternal inflation predicts bubble collisions. The cold spot might be evidence, or it might be statistical coincidence. In a large enough dataset, rare events occur. The cosmic microwave background covers the entire sky, millions of data points. A few unusual features are expected by chance. The cold spot might be one of them. Nothing more. No deep physics. Just random fluctuation. Current data cannot distinguish between these possibilities. The cold spot remains anomalous, unexplained, a puzzle written in the universe's oldest light. What makes it significant is what it represents. Cosmology has become incredibly precise. Models match observations extraordinarily well. The universe's history is mapped from seconds after the Big Bang to today. Most features are explained, but the cold spot doesn't fit. It's an outlier, a hint that something is missing from our understanding. Maybe it's nothing. Maybe it's a window into new physics. We won't know until we have more data, better observations, deeper analysis. For now, it stands as a reminder that the universe still holds surprises. Even in the most thoroughly studied datasets, anomalies appear, questions remain unanswered. And those questions become more urgent when we consider the universe's ultimate fate. Fast forward 1 trillion years. The Milky Way and Andromeda have merged into a giant elliptical galaxy. Most stars have burned out. Only faint red dwarfs still shine, using fuel slowly, lasting for trillions more years. Look up at the night sky from a surviving planet in this future galaxy. What do you see? Almost nothing. The cosmic microwave background has cooled through expansion until its temperature is nearly absolute zero. Photons have stretched to wavelengths longer than galaxy clusters. They're undetectable, gone. No evidence of the Big Bang remains visible. Other galaxies have vanished. Expansion has carried them beyond the cosmic horizon, not just beyond where we can currently see, beyond where light can ever reach. They've crossed the event horizon. They exist somewhere, but they're forever disconnected. No light from them will ever arrive. No signal can bridge the gap. They've vanished into permanent darkness. The observable universe, from this future perspective, contains only the local group of galaxies, maybe a few dozen galaxies total. Everything else is gone, erased by expansion. Future astronomers will observe this small cluster and think it's the entire universe. They'll have no evidence anything exists beyond, no way to discover the truth. Their cosmology will be primitive by our standards. They'll see galaxies. They'll measure distances, but they'll have no cosmic microwave background to study, no distant galaxies to observe, no redshift data to analyze. They'll think the universe is static, small, eternal. Every conclusion will be wrong, yet they'll have no way to know. The evidence has been erased. This is the future expansion creates. Not destruction, isolation. Each galaxy cluster becomes an island, completely alone, unable to communicate with other islands. Unable even to know other islands exist, the universe fragments into disconnected pieces. Each piece experiences its own isolated reality. Within each island, physics continues. Stars burn, planets orbit, perhaps civilizations arise. But they'll never discover the universe's true nature. They'll never learn about the Big Bang, never understand expansion, never realize they're isolated. They'll think their small cluster is everything. They'll be cosmologically blind. Some physicists find this troubling. We live in a privileged time. The universe is young enough that structure is visible, old enough that complexity has emerged. Future civilizations will miss this window. They'll lack the data we have. Through accident of timing, they'll be denied knowledge of the cosmos. Others argue it doesn't matter. If isolation is inevitable, worrying about future cosmologists is pointless. The universe doesn't care about knowledge. It doesn't care about observation. It simply evolves according to physics. We're lucky to exist when observation is still possible. That's enough. But the isolation continues beyond even this scenario. In 100 trillion years, red dwarfs burn out. Stellar corpses remain, white dwarfs cooling slowly toward absolute zero. Neutron stars spinning silently. Black holes evaporating through Hawking radiation. Over timescales so long they defy comprehension. 10 to the power of 100 years. Google years. Numbers that make billions seem infinitesimal. Eventually, even black holes evaporate completely. The universe becomes a thin soup of elementary particles. Photons, neutrinos, maybe some hypothetical particles we haven't discovered. All separated by distances larger than the current observable universe. Nothing interacts with anything else. The universe reaches maximum entropy, heat death, the end of complexity, the end of structure, the end of everything interesting. This is not a dramatic end. No big crunch, no big rip, just slow dissolution, gradual spreading, eternal expansion carrying everything apart until nothing remains connected. The ultimate fate of a flat universe dominated by dark energy. And it all begins with the simple truth we avoided for so long. The truth about edges. We asked where the universe ends. The answer is both simple and profound. It doesn't. There is no edge, no boundary, no wall at the end of space. The universe either continues infinitely in all directions, or it curves back on itself like a higher dimensional sphere. Either way, there's no edge to find. The observable universe has a boundary, 46 billion light-years in every direction. But that's a visibility limit, not a physical barrier. Space continues beyond it. Galaxies exist there, and stars burn, planets orbit. We just cannot see them because their light hasn't had time to reach us yet. Even the event horizon, the boundary beyond which we can never receive signals, is not an edge of space. It's an edge of causality. Space extends past it. The universe continues. We're simply disconnected from those regions by expansion. They're real. They're there. We just cannot access them. This realization changes everything. The question, where does the universe end, is based on a false assumption. It assumes the universe has an end. It doesn't. Space doesn't terminate. It doesn't stop at some cosmic wall. It continues. How far? We don't know. Maybe forever. Maybe just farther than we can observe. But definitely beyond any edge. Think about Earth's surface. Travel in any direction. You never fall off an edge. You never reach a boundary. Earth's surface is finite, but unbounded. The universe might work the same way. Finite in volume, infinite in continuity. No matter where you go, space continues. You never encounter an end, or the universe might be infinite, truly endless, galaxies extending forever in all directions. No matter how far you travel, more space lies ahead. No edge exists because there's always more. Infinity has no boundary, no stopping point, no last galaxy. Both possibilities are consistent with observations. We cannot distinguish them. The universe is too large. The observable region is too small a sample. We see flatness. That means infinite or very large. But we cannot tell which. What we can confirm is this. We live inside a bubble of visibility, our observable universe. Within that bubble, we see structure, galaxies, voids, filaments, the cosmic web. Beyond that bubble, the universe continues. We cannot observe it, but it exists. We thought we were searching for an edge, an ending, a place where space stops. But that was the wrong question. Space doesn't stop. It doesn't end. Our ability to observe space ends. Our causal connection to distant regions ends. But space itself continues. The universe is not a room with walls. It's an infinite or near infinite expanse. We're embedded in it. We observe a tiny fraction. Most of it lies beyond reach, beyond observation, beyond interaction. But it's there, real, vast, possibly infinite. This is simultaneously humbling and awe-inspiring. We are incomprehensibly small. Our galaxy is one among trillions. Our observable universe is one tiny bubble in a possibly infinite whole. Everything we've ever known, every human who has ever lived, every civilization that might ever arise, occupies an infinitesimal fraction of reality. Yet we figured this out. We measured the cosmos. We determined its shape. We calculated its age. We mapped its structure. We discovered we live in a universe with no edges. A cosmos that extends beyond imagination. A reality vaster than our minds can truly grasp. We were wrong about where the universe ends. It doesn't end. There is no ending. Just boundaries to our knowledge, limits to our observation, horizons beyond which we cannot see. But space continues. The universe continues. Forever. In all directions. Without edge. Without boundary. Without end. You are standing on a planet in a galaxy, in a supercluster, in an observable bubble, in a possibly infinite universe. Right now. This moment. Existing in a cosmos so vast that most of it is forever beyond your reach. Hidden by light's speed limit. Locked away by expansion. Separated by distance so great it becomes meaningless. We searched for an edge. We found infinity.